Okay, Assalamualaikum and good afternoon. So welcome back. So I think I promised to give you some quizzes, but I just didn't have enough time, so I'll try to prepare it within this week. So let's go to the lectures. So we stopped somewhere at almost at the end of lecture. Coming in. So we stopped lecture 2 somewhere at the end. So let me go to that. So we are on power series, and then I think we are looking at application. One of the application was to look at how we approximate functions. Just check. So we looked at how we approximate functions using power series, and we can see how close it is. And if you know precisely which interval that you want to approximate the function is going to be, then you can actually try to do the graphs, okay, and then essentially you can see that, okay, from this point to this point, it's already good enough to use, I think this is the 4 power series, okay. So now ready to use the 4 power series to approximate the function. Of course, it would not get the others, but no, that is already close enough. Okay. So today we continue with the thing where we are stopped. There are cases where knowing what power series of the functions that we want to evaluate can help us understand why certain computers give you wrong answers. Okay. Here's an example is given by the difference of two functions, okay, which is the log of the square root of 1 plus x, 1 minus x. Okay, so the square root is on the argument of the log. Okay, let me just show you. So that this whole thing is actually square root. So in other words, it's that thing. Okay. So and then take the difference with tangent x at a particular point. So if one were to calculate this using, say, calculators, for example, you can do this. Please try this at home. I'm not sure whether people are getting in or not. So let me just check. You can try this where you plug in your functions, log of this square root, and then minus tangent of this variable at the value of x equals to 0.0015. You should be getting some answers like this. With my handphone, it was something like, let me just check. With my handphone, it was I was getting the answer of 6.6160 times 10 minus 16 using a mobile phone calculator. Now, the answer is not that. Okay, the answer is the actual answer is given here. Okay, so why is this happening? Is because when you use certain computers or certain programs, for that matter, or calculators, much more worse is calculators, then they have rounding errors. Now, if you evaluate your log function using power series. Okay, so that means you have this difference between the two terms, and then you evaluate the individual terms first before taking the difference between the two. You can see over here, for example, it's almost the same until this decimal place. Okay, so this is tangent x. Oh, remember that you have to use radian. Okay, so in maths we used radian instead of degrees. So this is, oh, actually it's much more than that. So it's somewhere 25001. Okay. And it's over here. Okay, you can see they are the same. The values are the same up to I don't know how many decimal point. I think it was 16. Okay, should be. And then the rest after that is going to be different. So if you are already rounding error at one of this particular term, you probably get an incorrect answer. Okay, so if you do it using power series, for which you can do it for the first, say, 7 to the 7th power, for example, okay, then you get the correct answer is about 5.0625 times 10 minus 16. Let me just check people coming in. Okay, so I was wondering also whether Wolfram Alpha is any more intelligent than the calculator. So I did it on Wolfram Alpha, and it happens they are giving you the right answer. So this is something that I calculated just before the lecture. So you get 5.6252 times 10 minus 16. In principle, you have the professional version. You can actually add more digits, but no, it will take some time because it's a complicated calculations. But no, that's what you get. So, and that is already close to the numbers that you compute using power series. Right. So that's one of the things that one should always be aware of. Computers are just dumb machines. You just if you just assume that it's a black box, then if you do some computation without knowing precisely what is actually doing, then you might get wrong answers. Okay? So these are the things where you need to know all this mathematical stuff to help you understand the mathematics behind all the programs and computations that you do in softwares. Okay. So another application would be, if you remember, we did a few times, I think, L'Hopital's rule. Okay, why does it work? Okay, so when do you apply L'Hopital's rule? Okay, the L'Hopital's rule, let me just go down, is when you have problems where you get things like, sorry, oh dear. I always have this problem with my, so I have to, can I do this? No, not yet. So I have to unplug it and plug it back in. Okay, hopefully this works. Okay, that's what. So so when do you apply L'Hopital's rule? So remember, you use L'Hopital's rule when you have cases of indeterminate form, for example, 0 divided by 0 kind of thing, or infinity divided by infinity. So if that's the case, we apply L'Hopital's rule instead of evaluating the function at the limiting point. Okay, you use the derivative instead. Okay, the assumption here is, for example, is 0 divided by 0. The assumption here is when you take x equals to a for f of a and g of a, they are both giving zeros, and that of course becomes indeterminate. But if you take the derivative, what's going to happen? Well, this is what's happening. Okay, if you Taylor series expand both f and g, so what's going to happen? You have all these what we call functions and the derivatives evaluated at a. So if this is 0, this is 0, that's fine. You still have this. Okay, and of course, if you don't take the derivative, this you still have x minus a. So that means when you put x equals to a, this gives you 0. So that's why we need to take the derivative. So when you take the derivative of x with respect to x is just 1. So you'll be able to get f dash a, g dash a. Okay, so this is after taking the derivative. Okay, so when you substitute a inside there, oh no, this is not after taking the derivative. This is after, sorry about that, this is after taking f of a equals 0 and g of a equals 0. Okay, so in other words, this term is gone, but you still have the rest of the terms. But now you take the derivative. So this is the after taking the derivative, after taking first derivative. So you take the first derivative, then dx will be 1, and similarly at the bottom, and you're left with f dash a, g dash a, which is that. And this one, if you take the derivative, I should be writing not 2 factorial here, but I should be getting 2 times, sorry, this is a mistake again, so we should be correcting this. Okay, 2 divided by 2 factorial, okay, x minus a, f double dash a. So when you plug in f x equals to a, this will be 0. Okay, so in other words, in the end, what you will have is just the derivatives of f and g, the first derivative, evaluated at x equals to a and g equals to a. Okay, so that's why L'Hopital's rule works. And even if the first order derivative is actually 0, just like your functions equals 0, okay, then you can still use the same technique, taking the derivatives of the resultant power series over here. Then you should be getting, for example, this is the same as limit of x goes to a of f double dash a, sorry, f double dash x, sorry, over d double dash x. Okay, double dash means the second order derivative. So these are things which are made possible by using power series. Okay. Now there are other things like one of the things that we're going to cover in this particular course, right at the end of the course, hopefully we'll get there, is to solve differential equations. So sometimes you have differential equations related to some power series, and that's where you need to be able to understand power series quite a lot. Okay, and then the other applications of power series is to look at identities, okay, and then estimate bounds and values for integrals and other expressions. Here's a neat example, which is, I'm not sure where I got this from, but I don't think it's from Boas. But here is an example where you prove your number e, which is actually exponential 1, is really an irrational number. Probably in school you learn about how square root 2 is irrational, right? You know how to prove this? It's an easy proof for this one. But for the exponential e, it's also a irrational number. So how do we prove it's going to be irrational? So let's assume the opposite, which is saying that e is going to be irrational. So e is going to be an integer or divided by another integer with no common factors. Okay, and of course we would like to have p and q greater than 2. Okay, because 2 is already a prime number. Okay. What am I supposed to say? What else? Oh, it's not because of prime numbers, sorry. This is because, no, if you look at what is the value of e itself, it's 2.7 something, I can't remember. Okay. So you look for those numbers greater than 2. So, and let's assume that we can expand the power series for exponential, which is, in this case is exponential 1, and then this is really the expansion of power series, and then you terminate it at some term. So here is the qth term, and the rest will be counted as an error. So this is an error term. Okay. So this is really what we call the partial sum before this. So partial sum plus the error term. Okay. So okay. The error term here is estimated by some number x, ex over here, where x is must be less than 1, so that you get the decimal places in some sense. Okay, so you get some term here which with the x less than 1, so that it gives you the error terms of your expansion here. Okay, so let's take the difference between this number e here with the partial sum, so you get e minus sq, and that should give you the error term. Okay, and remember the hypothesis here was to think of e to be your fraction here. Your sq is just your partial sum here, and then what we're going to do is to multiply this with q factorial, because we have assumed that the denominator here that's supposed to represent e is q, so you multiply it by q factorial, so you get q factorial times p over q times q factorial times this partial sum. Okay. I'll be getting q plus 1. No, that's fine. I should be just having q here. So here you have q factorial over k factorial. So and k runs from 0 to q. So what's going to happen in this particular case? You'll see that, okay, what is this? Sorry, this is a mistake. This confused. This is really e to the x. Okay, so what's happening over here is this can be Okay, guys. So I'm getting confused with all the mistakes coming in. So here is the left hand side. Okay. So the left hand side is this one, and then you have the right hand side, which is over here. Okay. So the right hand side you have e to the x over q plus 1 factorial, but now you remember we have to multiply with q factorial. So you get q factorial divided by q plus 1 factorial, so that cancels out to q plus 1, and then you have your exponential x, which is some number that represents an error term. Okay, and then because let me just check. Okay, I have to make sure that this is right. If you look at what's the number e to the x, so let's go to Wolfram Alpha just to check this out. Okay, let's do this. Can you see this? Can you see it? The Wolfram Alpha. Okay, good. So if we just look at exponential 1, that's the answer, right? Let's see, we just make it slightly less than 1, say 0.99. So its difference is around, no, okay, let me just take the difference between the two. Okay, so it's much, well, it's less than 0.1, okay, put it that way. So in other words, going back to the lecture notes, so whatever this number is, okay, it's going to be less than, how should I say, it's going to be less than e to the power of 1 divided by q plus 1. And remember that q plus 1 is, no, you stop at q at some specified q, which is quite high in the expansion, but that is at the denominator, so this will be less than 1 over 2 plus 1. So in the end, what's going to happen? We know that this error term is going to be greater than 0. Okay, that's the error term. Okay, and then from this, you can evaluate this. This is less than 1. Okay, remember that e is actually 2.73 something, okay? And then divide by 3, that's less than 1. So if really your, if your number exponential exponential 1 e, okay, is really actually p over q, then when you multiply q factorial over here, it should be an integer, okay, because this is much bigger than that. Okay, so whatever this is, this will dominate sort of, and then convert this rational number that you assume to start with into an integer. Okay, but then if you look at what the conclusion is, you are getting an integer. Your q is integer, which is between 0 and 1. There's no integer between 0 and 1. So in other words, the assumption that we had earlier saying that your exponential or e to the power of 1 is actually a rational number is actually wrong. Okay, so that's how you actually, this is what we call a proof by contradiction. Okay, so okay, so that sort of finish off your second lecture. Are there any questions at this particular stage? I believe I've uploaded lecture 1 and 2 before, and just this morning I uploaded lectures 3 and 4 in the notes. Any questions so far? Or should I proceed? I guess no. Very quiet. You have to know. Sometimes I need to know whether you are still there or not. Okay, so just say yes or no. Okay, and somebody's leaving the meeting. Okay. All right. Okay, never mind. So next do is again. If I look at Boas, I think it goes into complex numbers. I'm going to do slightly, no, the way I do things, I tend to, I don't like to follow directly what Boas is doing. I do follow it in the sense that, okay, if chapter 2 is complex numbers, I will, I will give lectures on complex numbers. But sometimes the way I think about complex numbers is probably different from how some other researchers or other scientists would think of it. Okay, physicists for that matter. So I would like to make some awareness kind of thing. What is really numbers? Maybe I should be slightly more philosophical and ask students questions. Need some feedback from you. What do you think about numbers? Are they real? Are they something which is reflecting nature in a way? Anyone? Any opinions? Are you still around? So what do you think of what is it the thing, yeah, what is the thing that you call numbers? Do you think it's something real or it's just a figment of imagination? Okay, that's is an unfortunate way to label complex numbers with real and imaginary, but let's take just ordinary numbers, natural numbers, for example. Are they real? So are they something physical? True, that's good. In some sense, okay, the numbers do come from physical ideas. Okay, for example, natural numbers are essentially generalization of how we count. Okay, like the command that I just read just now. Okay, so what mathematicians try to do is to do abstraction. Okay, so if you start counting, it doesn't matter whether you count the number of pencils or the number of chairs. The number is still, say, if you have 10 chairs and you have 10 pencils, that number 10 is still referring to a quantity. So in other words, it's an abstraction, and that abstraction sometimes it causes some philosophical debate, okay, to the point of saying whether mathematics is actually what they say, is it invented or discovered? If it's discovered, it's something intrinsic to the world. If it's invented, it's just our way of making sense of what there is in nature. Okay, so there are a lot of debates on this particular topic, but I will not go into it because I don't want to bore you. But the idea is started with an abstraction of counting, so we call it numbers, natural numbers. Okay, And even with natural numbers, do we include 0 or not? What do you learn in school? Can I get some feedback? Does natural numbers include 0 or not? To your understanding? Pretty quiet. Now, there is a reason why I'm bringing this up, so that you can see how mathematicians think about, or how physicists think about some of these things you know about numbers, okay? So that you really have that what you call feeling for numbers, okay? So is 0 inside natural numbers? That's my first question. Second question, right? Why? Well, okay, even the other mathematicians, pardon? Well, that would be integers. Integers are different from natural numbers. So even in the community of mathematicians, there are debates whether they should include 0. So let's just leave that. So for me, I would, when you count, you don't count from 0 unless you count backwards. Okay, so you always count the number 1. So 0 is actually a very relatively recent kind of abstraction. I think it began in the Indian civilization and then got picked up by the Arabian civilization. Okay, so it's not something that's already there in the Greek civilization, for example. Okay, and then associated to the natural numbers are no. You have all these operations, the mathematical operations of, for example, you know how to add two numbers, you know how to multiply two numbers, and they give you the same, no, the same object, which is natural numbers. Okay, but when you consider the inverse of this, what's the inverse operation? Well, the inverse operation. In the sense of addition, in the sense of addition is subtraction. So it's something like this. X plus minus x gives you what we call 0, which is what we call the additive identity. We will learn all about this thing later on. That's why I'm introducing it now, so that you can actually see it. So when you have this additive identity added up with the number itself, you always get 0. Or you take the additive identity, add to a particular number, you get x. It doesn't do anything. It gives you the identity. Now there is another identity, which is a multiplicative identity. So you multiply x with 1, you get back x. So you can see the analogy here. Here is the additive identity, 0. Here is the multiplicative identity. Now, to see an inverse operation, you must find a number in such a way that when you add it, you get the additive identity. Just like multiplication, for example. What is the inverse what you call operation here would be so what you want is essentially when you combine this operation together, you always get back the identity. In this case, your identity given by multiplication is 1. Okay, so over here the identity here is given by an inverse operation, which we call as subtraction. Here, the operation which is inverse to multiplication is what we call division. Okay, I hope you understand that. So now what happens is numbers get generalized. You start with something which sort of an abstraction of counting, but then when you include operation of addition and its inverse, then you have to include negative numbers. Okay, so now when you include negative numbers, okay, we have what we call the set of integers, which is given by the symbol z. I think the symbol z is corresponding to a German word called Zahl. Okay, which is, I think it means something about numbers. I can't remember precisely. And then if you can multiply, you have the operation of multiplication on natural numbers. Then if you include the inverse operation, which is a division, then you get rational numbers. I'm not sure why it's called Q, but no. Q is meant for rational numbers. But then you also already know that when we did the exponential just now, okay, the e to the power of 1, that besides rational numbers, there are numbers which are irrational, right? So when you complete these rational numbers with irrational numbers, then we get real numbers. Okay? So again, these are all generalizations. We started off with natural numbers, we generalize, we get integers, we generalize again, we get rational numbers, and then we generalize to include irrational numbers, we get real numbers. And real numbers, what happens is supposed to be thought of as a continuum. And how do we represent this continuum? We represent it as points on the line, or points on this line, for example. Okay, so in a way, you know that lines exist in nature in some sense. Okay, you take a particular, say, the crack on the wall, or the connection between the wall and the ceiling, you get a particular line. Okay, so they are physical in that sense, and we make it abstract, and we construct what we call okay, that line can be represented by real numbers, the continuum. Okay, so in a way, this is the kind of picture that I hope that you get the idea. So the number system, the real numbers, for example, they are not real in the real sense. They are constructed, but you can say that, okay, this corresponds to some real things. Do you get what I'm saying? Any question at this point? Because I'm going to introduce something a bit more controversial in some sense. Okay. Do you have any question at this particular stage? So what I'm saying, your real numbers are really being constructed rather than something which is actually physical. Okay. Okay, it seems very quiet. Never mind. So now, well, are there numbers beyond real numbers? Of course there are. You have learned about complex numbers. But in fact, can you generalize beyond complex numbers? Let me just give you the short answer, yes. There are other numbers which I don't want to give you the definitions at this particular stage. There are what we call quaternions. and there are what we call octonions. They are numbers in the sense that they are mathematical objects that can be defined with a division. So sometimes it's called a division algebra. This is just for your no, I mean, people are investigating all these features of what constitute a number. Okay. So, okay, let's not get too far from that. Okay, let's consider the case of a quadratic equation. Now, I write this quadratic equation using z. Z is already, usually people associate this with complex numbers. But think for a moment like your z is like your real variable. Okay, so if I give you this algebraic equation, okay, and equate it to be equal to 0, so you find the roots. Okay. What are the roots? Well, you know that you have the famous formula, the quadratic formula for the roots, right, given by this. Now, normally, because of the square root inside this thing, okay, under this square root is called a discriminant, so the b squared minus 4ac is called the discriminant. This discriminant are usually assumed to be positive. Correct? Anyone? Am I correct? Yes, doctor. Okay. This somebody. No, because once I put my screen up, I don't see your chat essentially. So you should try to talk, put a message on. Okay. So So in other words, what we have this condition where if you remember what is a quadratic is actually represented by a parabola. Okay. And the cases are depending on whether you have situations like this, then the roots will be here. This is the case when b squared minus 4ac greater than 0. So when you have this thing to be positive, then you get these two different signs, plus or minus. Okay, so you get that. Okay, the two roots. If you get b squared minus 4ac to be equal to 0, then you have this situation where this falls. Okay, my diagram is not so good. So this falls on a single root case. This is the case of b squared minus 4ac equals 0. Right? So this is, okay, this is the curve of f of z. This is the curve of f of z. Okay. Now you can see that, okay, this sort of make some sense about the numbers of the root, but also of the equation over here, this particular quadratic equation. Now there's one diagram missing from these two. And the diagram is what? Well, the diagram is given by this kind of diagram. This is the thing I mentioned. So we have this diagram, which is not included in what I've just mentioned. Okay? And this diagram is associated to the complex numbers. Why? This is the case of, if you look at, remember that this is the case of f of z. Okay? So f of z here is greater than 0. Okay? And this requires us Okay, this requires us, if you study the components quickly. Yeah, I did this no, sort of rough idea here. If you just look at the minima of the quadratic curve, okay, this height here is given by d over, let me just make this bigger, I cannot really see it, d over 4a. Okay, and where does it fall? It falls at z equals to minus b over 2. Now, if we look, what is precisely those numbers? Let me go up. This is precisely this number which you get from here, this part. Now, and then you allow b squared minus 4ac to be negative. Okay, and call that to be, and then you know that that will give you imaginary numbers, okay, which is an unfortunate label, okay, but that will give you a square root d over 2a. And you can see that, okay, this is related to the height. You take the square root of this, you get square root. Okay, maybe I'm a bit wrong here, so I have to check that, but okay, square root d over 2a. Okay, so maybe the a is not actually, okay, this is not the whole thing, so this should be square root d over 4. That's one. Okay, so you get square root d over 2 times 1. Okay, so in other words, what happens in this particular case, if you allow the negative square root to come in, you still can represent things in this picture. It represents something. It's like a physical thing. You consider like this curve is like representing some physical object in space, and such object actually represents, if you look at the properties of this and the properties of the points here and the height here, this corresponds to something which is related to the complex number. Okay, so that's the thing that I'm trying to sort of push for you to accept in some sense, that okay, your complex number is also as real numbers in a way. It corresponds to what we call a geometry of curves. So so you have learned about complex numbers before, right? So what is square root minus 1 is denoted as your I, and if you take the square of I equals to minus 1, and I cube is minus 1, minus I, sorry, I to the 4th, then you go back to 1. Okay, so it's a 4 full cyclic. Okay, so you take I to the 4n to the power of 4n is always equals to 1. By doing so, we are always able to solve this equation. Previously, we have the condition that the discriminant must always be positive. Now it doesn't matter. Okay, you can have your discriminant to be negative, you still find solutions to this, and the solutions are described by this curve. Okay, and what else do I want to say here? Oh yeah, the other thing is, if you start to, okay, so that is the quadratic. If you start to allow this imaginary numbers, which I said is an unfortunate term, and try to think of a function which is more beyond quadratic, for example, a naught plus a1z plus dot 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 a n and we will talk about complex functions later on. Okay, you can always find the roots of this equation. So that means if you put this equals 0, then you can always find the roots if you allow the extension of the real numbers to complex numbers. So that's why, just like previously, okay, the analogy here is what? Analogy here, irrational numbers complete rational numbers to real numbers. In the same way, previously you have difficulty to find roots if you don't allow the negative discriminant. Here it's also called, the complex numbers are called, where is it? It's always called the algebraic closure, just like the case of the real numbers. It's a different kind of closure. So this sort of completes real numbers in algebraic sense. Okay, so as I said, the point of view saying, okay, complex numbers, we have the real part plus imaginary part, and the fact that we call this imaginary part is really unfortunate, because that imaginary part we can actually represent it in cases like this. Okay, so it's not really imaginary in that sense. Okay, it's just something that we have to get used to the idea of a square root of the negative number. Maybe there are questions at this stage before I move on, because I believe you have done complex numbers before, right? Can somebody confirm that? So, but have you seen this kind of interpretation? Yes or no? That's only the answer that I want. If yes, it's good. If no, then I hope you learned something new today. Okay, so in other words, your complex numbers, which involve the so-called the real part and also the imaginary part, there's nothing really imaginary about imaginary. It's also as real as the real numbers, if you know what I mean. Okay, so the way I see things is, if you can represent it in terms of a geometry, so in this case, geometry of curves, okay, then it's real. Just like your continuum, which is represented by a straight line, okay, your irrational numbers, you know how difficult to represent irrational numbers? You have an indefinite decimals, okay? But yet, no, you feel it's real because you can represent it on the line, right? So anything that you can represent sort of geometrically in some sense, no, it's not any different, okay? Okay, let me just go see. If we do have, please shout, okay? Because I think, no, we need to interact more in the class. Okay, so you have done how to construct, for example, complex numbers. For example, you take square root of minus 36 is just you take the minus 1 times 36, and then the square root of 36 is just 6, and then square root of minus 1 is I. So those kind of things, I hope everyone knows about it. And then we had this unfortunate thing that we call the real part and the imaginary part, but for me it's both as real as the real. Okay. Okay. the fact that there are two components to the complex numbers is like a coordinate. Okay, so that's why the other kind of picture that one should have is to consider just like the real line represent the real numbers. So the complex numbers, I should do it the other way. Okay, so maybe I should put a double arrow instead. So the real numbers you represent it by a continuous real line. What about the complex numbers? Well, the complex numbers, you can represent it by a plane. So this is 1D. Here you have 2D. Okay. So, in a way, there is various way you can think about the complex numbers. One is to think in terms of what we call the Cartesian representation. So you break it up into two parts, where x is the real part of z. Given that z equals x plus iy, then x is the what we call the real part, and y equals the imaginary part. So we have to stick with those terms which are already familiar to most people. So we stick with the imaginary part. Okay, but I can think of this just like your coordinates. Oops, not a straight, not really vertical line there. Draw it properly. And this side. Oh, because I'm having my pad at a different place. So, never mind. So here's your x-axis and y, because I'm doing it slanting here. So I can start to think of, okay, I'm representing this number z using this kind of coordinates. So I get the real part and I'll get the imaginary part. But you can see if I collect all these possible points of imaginary part and real parts, they're actually forming a plane. So that's why we say that, okay, it can be represented geometrically as a complex plane. And being in a plane, then you start to think, okay, when I use coordinates in two-dimensional plane, I can represent it differently. Okay, then I can start to do change of coordinates. So one of the things that we already learned very much is that, okay, I have the Cartesian coordinates x and y, but I can also represent this point, for example, on the plane by the polar coordinates. So I measure the angle theta coming from some axis here, so usually taken as x-axis, and then I measure the distance to that point. Okay, and the conversion is known. X equals to r cos theta. This r cos theta. What do you call this? Adjacent over hypotenuse, right? And then opposite over hypotenuse. So you get your sine. And if you combine these two in terms of polar coordinates, you have something which is related to cos theta plus I sine theta, and that later on we shall see that this can be written in terms of an exponent, but an exponent of a complex number. So we'll come to that. This is what we call Euler's formula. I believe that has also been taught to you somehow. Okay, but now a much more less familiar too many, but no, I mean, is the inverse relation. So here from x goes to r and theta, y goes to r and theta, but r goes to x and y. Of course, this is a bit more familiar, but theta is an arctan of y over x. Arctan is the inverse function of tangent. And the inverse function has no problems because there are cases where you might get singular points. Okay, in this case, when x goes 0, then you get arctan infinity. So what is arctan infinity? Well, theta is actually arctan infinity is what? Pi over 2, tangent 90, right? So there you get arctan infinity. Okay, so in other words, everything seems fine at this particular stage. The only thing is, okay, whether we want to use the Cartesian form or the polar form. Okay. Now, there will be advantages when you do Cartesian form, and there will be disadvantages as well, and there will be advantages using the polar form, and there will be disadvantages as well. Okay, so we need to know when precisely to use a Cartesian type of representation or a polar type of representation. This one is another thing. In maths, we tend to use radians. Okay, so the fact that you use radians is because then it makes sense for you to have this kind of limit. Okay, then if you try to do it with the concept of degrees, that is no longer really true. Okay, degrees, if you really go back where degrees come from, this is coming from, I think it was probably Babylon era. Okay, if you look at how's the number system looks like. No, you go from 0 to 360 and then you go back to 0 again, right? This is a different different number basis kind of thing. Nowadays we tend to not use this. Apart from one single place, we still use this Babylonic kind of number base, which is really your time. If you look at time, you talk about 60 minutes, gives you an hour, 60 seconds, give you what you call 1 minute. Okay, you're stuck with that. We don't have a real metric version for that time unit. But never mind. But that's another point. The idea here, your radian is better because it's actually a ratio of length. So in other words, radians are dimensionless. Degrees are not. Okay, so that's the thing that one needs to be careful about using those numbers. Okay, right. Okay, these are all probably well known to you. You're supposed to know how to convert from Cartesian to polar form. Okay, so remember the formula. So this is x, this is y, so r is just square root of x squared plus y squared. But the much more difficult, well, it's not that difficult, but the more trickier is the case of your angles. You need to be telling you, okay, it's y over x, yeah, but then you have to make sure where does this live. you remember, we can break up the plane into 4 parts. Okay, there is the case of x positive here, y positive here, and then here is x negative here, y positive here, and then here is x positive, y negative, and here is x negative, y negative. And you have to make sure that, okay, whatever angle that you choose, it corresponds to the right quadrant. So here is y and x is in the positive quadrant. Then you look for the angles that correspond to that particular ratio, and that is actually equals to pi over 4. Okay. Otherwise, you need to go to the quadrants. Okay, use some conversion thing. Right. Okay. So in other words, your polar form is given in terms of this, in terms of an exponent. Okay. So what are the things? Again, this is pretty boring. So these are again another example of Cartesian going to polar. So you calculate the radius, so to speak, and then calculate the theta here, and then here it makes it's a bit different because your y is positive, your x is negative. Then you have to look for this particular angle. Okay. Okay. Those, I assume everyone is probably familiar. The other one that's supposed to be familiar to you is that there is an extra operation when you deal with complex numbers, which is what we call the complex conjugation. To be specific, because there are other kinds of conjugation, but never mind. For short, we can call it conjugation. Okay. So what does it do? Essentially, it gives you, you define z equals to that, then you define your conjugate to be z star or z bar, depending on the situation. We use interchangeably these two notation. Then you replace the imaginary part from a plus sign to a minus sign. Okay. And what happens when you do in terms of polar form, again, if you look at this, you can see that you just look at what multiplies I, turns into a minus sign. Same thing here, what multiplies I over here turns into a minus sign. So it's the same in both the Cartesian representation and also in the polar representation. The reason is because the polar representation is coming for x it's r cos, and cos is actually even function, and for y is r sine, and this is an odd function. We'll learn about this probably later on. Okay. So I hope you are familiar with those. And then, okay, so I learned how to convert complex numbers into different types or different forms, different representations. Can you do other operations? Well, like I've said before, in the case of numbers, you have this already. For the case of real numbers, you have your addition, you have multiplication, but you also have what? You also have subtraction, and also your division. So if complex numbers are a generalization of real numbers, then all these four should also be definable in the case of the complex numbers. And indeed, this is true. Let's take the basic operations first, the plus and the multiplication. So the plus sign, what happens is that, okay, I get your real part added up and your imaginary part added up. Now, what about multiplication? Okay, that looks easy, right? What about multiplication? Suddenly, your multiplication becomes something very different. If you think of, say, let's say a real number, right? Real number 2 times 3, okay, because 3 times 2 goes to 6, right? And then, so I can represent this generally as x times y, y times x. Okay, so if I have two numbers, x and y in this case, then no, I just multiply it straight. Okay, but here you don't. If I were to use this kind of technique, then okay, let's have your z to be represented by xy in this form. Okay, this is a bit confusing. Maybe I should write it this way. Let's do, okay, let's write this as x1 x2 equals to x2 x1, because they are on the real line. Okay, so now let's consider the case if you extend this idea. Okay, maybe I can now write your z as the coordinates x and y. So if this is z1, then this is x1 y1, z2 is x2 y2. Then if I try to make sort of a simplification of what we have over here, then why shouldn't it be something like this? x1 times x2, comma, y1 times y2. Why do we have this combination? Now there's a reason why, because if we do it this way, some operation of division has a problem. Okay, maybe later on we'll look at some exercises. Okay, so in other words, inverses has a problem when you define multiplication in this particular way. But what's needed is something like this. Okay? Or in terms of the coordinate form, this is something like x1 x2 minus y1 y2, comma, x1 y2 plus x2 y1. This will be your x coordinate of z1 z2. This is your y coordinate of z1 z2. Okay, so why is this happening? So again, this goes back to a longer picture of what is a division algebra, in a sense that you need always to find multiplicative inverse to non-zero numbers. Okay, that would fail for the case of this. Given a non-zero number, then you can always find inverses multiplicatively. Okay, this combination does not work. This combination does work. Okay, so that's why you have this slightly more complicated multiplication for the case of the complex numbers. Okay, but okay, having said that, you can see that okay, using the Cartesian components or Cartesian representation, your multiplication is a bit more complicated, unlike the case of the addition. The addition is, it looks simple in the context of Cartesian representation. Okay, but it looks complicated in the case of multiplication. But look at this. When you convert to polar form, this is your multiplication, and this looks easier compared to this. if I really want to put this, I should be telling you how to take the addition formula of cos theta, one cos theta with another cos theta, and the same over here. You can find a much more what we call okay, what I'm trying to say here, try to put this here, you see as two terms, right? Try to put this in a single term. Rather than having separate terms like this. Similarly for this. And then you see that, okay, in the polar representation, your addition becomes complicated. Okay? Your multiplication becomes simpler for the polar form, but your your addition becomes complicated. For the Cartesian case, your addition is simple, but your multiplication is difficult. Okay. Okay. I think I want to. What's the time now? 3:22. Probably we take a short break at this juncture. I should have taken the break just now. Are you still with me, or have I lost the connection or something? Okay. So we'll take a 5 minutes break. Okay. Okay. I hope everyone's back. Can we restart? Great. Right. Okay. Again, I hope you don't mind going through all this basic stuff. No, I know that you've been exposed to complex numbers before, but now no, it is a kind of revision. But now I want you to have this deeper understanding rather than just having know how to calculate things, for example. So with respect to operations of numbers, there are certain properties that we really try to make sure that they obey. For instance, what we call commutativity of addition. So that means when you take two complex numbers, actually this is true for all numbers. Okay? If you take two complex numbers, then if you swap them around, you get the same number. Okay, so this is what we call commutativity of addition. And if you know how to add two numbers, then you should be able to know how to add three numbers, because no matter which two numbers that you add first, then it's the same. The result will be just the same as, I can remove the bracket to show which operation is done first, and I can just represent it by just Z1 plus Z2 plus Z3. So that's what we call associativity of addition. And then as before, we have the additive identity. So I have that. So what is the additive identity? Is just 0. And then the additive inverse is just minus Z. And then for multiplication, then you have again commutativity of multiplication. Now this is also true for the case of the numbers, which is more special below complex numbers. All numbers numbers like what you call integers, real numbers, complex numbers will obey this. Okay, that means you multiply 2 times 3 or 3 times 2 is the same thing. Okay, just for your information, if you go one step more general than the complex numbers, you have the quaternions. yeah, you have the quaternions, there your commutativity fails for multiplication. Okay, but we are not doing quaternions here because you probably learned this at some other place. Okay, so you have commutativity of multiplication for complex numbers. Again, you also have associativity of multiplication. So that means it doesn't matter which two I multiply first, this will always give you the same number, and I can remove your bracket there. Okay, then the multiplicative identity is just 1, and then you have your multiplicative inverse. So for numbers, you always have these two operations of multiplication and addition. But once you have these two operations, you need to know how to mix them up. So here is the idea of distributivity of multiplication over addition. So if I have two addition of complex numbers here, then multiply by another complex number outside, then it will just give you, distribute that multiplication over the addition. Okay. What else? Then you have your conjugation. Okay, so the conjugation, this is pretty interesting in some sense. Your conjugation is again, you obey, if you think as conjugation as a different process, a different operation, then you see that this distributes over also the addition and also the multiplication. Okay, and then you also have the division, which is actually just an inverse operation of multiplication. And this can also help you do things if you know a particular function can be done in terms of power series. Later on we'll talk about that. So if I want to go to fz bar, then this will help you to just see that this is just simply fz bar. If this f can be represented by a power series. Okay. Okay. The other thing that's also available here is the idea of absolute value. This is actually just giving you your radius in the two-dimensional plane, which can be written as a square of your multiplication of z with z bar. Okay. So one of the things that we also learn, if you have 1 over z, for instance, what we normally try to do is to redo it in this particular form so that you get, you always are able to write it in terms of a real part plus an imaginary part. Okay, so over here, this is just what's the real part? It's x over x plus y squared. And then what's the imaginary part? Well, it's minus y over x squared plus y squared. If you put it in this particular form, you are not able to see this in a transparent manner like that. Okay, but of course you can always do this kind of operations. So you need to know how to do that. Okay, so I assume you have done this at some point. One of the things that one needs to be able to do with complex numbers is to solve an equation. Here's an equation, for example. Okay, I have x plus I y squared. Okay, supposed to give you a complex number there, and then this should be equals to 2ix. So how do you solve this complex equation? It's just to expand this. So when you expand this, it becomes that. It becomes, maybe I should not say that. When you expand this, becomes x squared minus y squared plus 2ixy. Okay. Write it down here then. X squared, sorry, not plus, x squared, sorry about this, x squared minus y squared plus 2ixy. Okay, and then on the left hand side, sorry, right hand side, you have 2ix, and then what you do, you try to rearrange the real part together, so I get x squared minus y squared only, and there's no real part for the left hand side. And then for the imaginary part, you have this imaginary part, and also this is also imaginary, so you have that. Okay, so this must be equals to 0 because you bring it on the other side, equals 0. And what is 0? 0 is simply 0 plus 0i. So I can now equate the real part. What's the real part? It's x squared minus y squared equals 0. And I equate the imaginary part, which is 2xy minus 2x equals to 0. So in other words, what we need to do is to find equations that solve this. And because of that, you are able to see several different solutions. This is just like taking the square, the roots of a quadratic equation. You might have multiple solutions. Okay, so here is the multiple solutions. Now you might say, where does it appear in physics? Well, one of the things that we have learned is to use complex numbers inside an electrical circuit. Okay, if you remember, I'm not quite sure where you learned this precisely, probably in electromagnetism or electronic circuits or something like that. Okay, you put you look at the voltage and the current around certain elements of the circuit. So for the inductor and the capacitor, the current might be well, for the resistor, for example, your voltage and current will be in the same phase, but in the context of say inductor and capacitor, I'm not sure which is which. Well, one is sort of go ahead, and then the other one is actually behind. Okay, but the idea here was to, you can, later on we talk about the trigonometric function. You can actually get it from this thing. Okay, so related to this, so you have this oscillatory motion of your electrical signals. Then you can actually see, okay, which one leads or which one lags the other. Okay, so the idea here is, now since we know how to do this for sinusoidal function like this, then you should be able to treat your voltage elements, or your electrical elements with the electrical signals as a complex number. And we have learned that for the case of inductor, it's given by, it has the, okay, here is what we call reactance. So the reactance is the form for which it follows the V equals to IR kind of formula. So you have your voltage of, about the inductor equals to the current times the reactance of the inductor. But the reactance of the inductor is actually given by omega L, where omega is the angular frequency of the sinusoidal signal. Okay, for the voltage around the capacitor, again, in this case, the reactance is just like the formula for V equals IR. Okay, so this reactance, but in terms of the what you call the oscillatory thing with the angular frequency, then this is actually I over omega c. Okay, so one could actually use this to your omega, remember, is like your complex number there, so one can actually use your complex analysis to actually do this representation of this electrical signals. Okay, and given that you have say the resistance and the inductance and the capacitance, one can combine all of this in a way that this is given in terms of reactance of the inductor, reactance of the capacitor, but with a phase difference of -1, with the phase of -1, okay, and then the whole thing is what we call the impedance of a circuit. So the impedance of a circuit is now represented as what you call a complex number. I hope you have seen this somehow. No, I mean, this is a real application of complex numbers in practical terms. So then when you talk about how do you put the inductance or the impedance in series or in parallel, then it follows the what we know for the case of the resistance. Okay? Then we can actually calculate this, replace this by complex numbers, and so on and so forth. I think here is an application here. Right. So here, this is resistance. This is capacitance, and this is inductance. Okay. So now we try to calculate the impedance of this circuit. First and foremost, there are two parts here. One is this parallel thing, but you can do the series of that first. Okay, then you get the following: Z1 and Z2, and then once you get Z1 and Z2 here, then you can do this thing in parallel, and then you'll get the case of the total case, okay, which is 1 over Z, okay, of the total, divided by the 1 over Z1 plus 1 over Z2. Then you take the reciprocal, then you get the total impedance of the circuit. Okay, this goes into a different topic now. Probably I want to stop at this stage. Is that all right? We have almost 2 hours, but there's another 15 more minutes. Probably I want to take this as a suitable point to end this session, but otherwise it will go on. And usually I don't want to make the recording for your lectures extend until 2 hours. Is that okay?
Okay.
Okay, so I'll stop there. Yeah? Sorry, I didn't hear the last comment. Okay, I suppose everyone's okay with that. So I will take the attendance now. Okay, that's done. So are there any immediate questions before I stop? Okay. So thank you, everyone. So I'll see you tomorrow, right? Tomorrow. Okay. Okay, bye, everyone.